Welcome to Lecture 37, in which I'm going to discuss applications of electromagnetic induction. Now, in the previous lecture, I introduced the theory of induction, that changing magnetism causes electrical effects, and I waved around my big bar magnet near coils of wire, and I had relatively puny effects like tiny movements of an electrical needle. I don't want you to go away thinking electromagnetic induction is some kind of puny effect, because in fact, electromagnetic induction is the source of nearly all the world's electrical energy. We generate electricity with electric generators. As I hinted last time, electric generators involve changing magnetic flux by changing the orientation of a coil of wire in a magnetic field. Let's take a look at how a generator would work. So here's a picture of an electric generator, and it looks very similar to the picture of the motor that I showed you a few lectures ago, and there's a reason for that. A generator and a motor are really the same thing, operated in reverse. Put electricity into a motor, you get out mechanical energy. Put mechanical energy in, spinning a coil of wire in a magnetic field, and electromagnetic induction gives you electricity out. So that's how generators work. So this picture looks very much like a motor. You can see the coil of wire that spins between the poles of the magnet. You can see a mechanism for pulling that electricity off from the rotating structure onto stationary wires and onto some load, which it then supplies with electrical energy. Generators are ubiquitous, and I have a lot more to say about generators. Let me just begin by giving you several examples. Here are generators in large-scale electric power plants. The one on the left at the top is in a steam-powered power plant, could be a coal or nuclear plant. You see great big pipes at the back bringing in steam that turns a turbine, that turns the structure in the front, which is an electric generator, spinning coils in a magnetic field. Similar generators in a hydroelectric station, and the wind turbine is a smaller example of an electric generator. The one on the left is probably generating about a gigawatt, about 1 billion watts of power. The ones in the upper right are probably generating a few 100 million watts each. The wind turbine might be generating anywhere from a few 100 kilowatts to a few megawatts, a few million watts. Well, let's look at a real electric generator in action. I have one sitting right here, and I'd like to invite Laura from the Great Courses to come in, and she's going to do some cranking on this generator for us. So what I have here before Laura starts is it's an electric motor. I bought it as an electric motor, but a motor and a generator are basically the same thing. I got some belt that drives the motor or generator back there, and I got some meters that read how much voltage and current it's producing, and I got some electrical loads I can switch in and out. So I would like Laura to start turning that crank, and crank it at a nice pace. And Laura, if you can, crank it so that voltmeter reads about 12. It's not crucial, but get it up about 2/3 of the way. So crank it nice and fast. Okay, pretty easy. So she's having no trouble cranking that generator. There she goes. Real easy. Just keep it going, just like that. Nice and easy. Keep going, keep going, keep going, keep going. She's spinning coils of wire in a magnetic field. But right now there's no current through those coils because I'm not asking them to supply power to any load. Keep going, Laura. Keep going. Keep going, keep going, keep going, keep going, keep going. Okay, now I've turned on a 100-watt light bulb, and it's really, really hard for her. And she felt that really sudden hardness of turning it. I'm going to turn it off again. Oh, much easier again. And I want you to think about that, because if you're worried about conserving energy and not generating as much global warming greenhouse gases or fossil fuel pollution or nuclear waste or whatever comes out of your local power plant, you want to minimize the hard work the power plant has to do. And every time you turn on a light, that power plant feels exactly the same oomph that Laura feels, and she has to crank that much harder. Now, maybe it'd be a little easier if I asked Laura to light a 50-watt light bulb. That's easier, right? So there we go. And just to make it even easier, you can light this one. Okay, there's a compact fluorescent. Produces the same amount of light, but with a lot less energy, and consequently it's a lot easier for Laura to crank. But she's still having to do work. And again, the reason she's doing work is the same reason I had to do work when I thrust my bar magnet at that loop of current. Because the coils in there have current flowing in them. The direction of the current is such as to oppose the induced effect that's the effect that's causing that induced effect, and consequently the permanent magnets in that generator and the moving coils become magnets that oppose each other, and Laura has to do work to overcome that force. It's no problem at all when there's no force involved, when there's no current, but as soon as I try to make her generate electric power, to make energy to light this light bulb, it becomes very difficult. And every electric generator feels that same oomph whenever somebody anywhere in the world turns on a light bulb. Thank you very much, Laura. Appreciate it. Okay, well, electric generators are used, as I say, to generate our power. Large-scale electric power generation, about 40% of the world's primary energy consumption goes into making electric power, although the process isn't very efficient, and so only about 12% of the energy the world actually uses is in the form of electricity, and it's generated, almost all of it, in electric generators. Tiny fraction in photovoltaic cells and other non-mechanical devices, but almost all of it in generators just like that one. But we use generators for other purposes as well. For example, in your car, there's a small generator. It's called an alternator because it produces alternating current. It's used to charge your car battery. In a larger version of the same thing, there's a bigger generator in a hybrid vehicle. Sometimes the generator in the hybrid is the same as the drive motor, and when you slow the car down, the wheels turn this motor, and it acts as a generator and recharges your battery. Hybrid vehicles also include, hybrid cars aren't the first invention of such a thing. Diesel-electric locomotives are in some sense hybrids. They use diesel engines to turn generators which generate electricity, which run electric motors which drive the train. Emergency power is another example of electric generators. So we use electric generators of all sizes in a lot of different applications, and they all share the fact that mechanical energy goes in and electrical energy comes out. And in principle, you'd like them to be 100% efficient at generating that energy. They're not 100%, but they're pretty efficient. They take most of the mechanical energy that comes in and send it out as electricity. The inefficiencies in power plants come in the conversion of thermal energy into electricity, as you saw in the lectures on thermodynamics. So those are electric generators, and let me just give you some other examples. I have here a couple of electric generators. Here's a fancy device. It's a hand-cranked flashlight. Has some rechargeable batteries in it, and so I have to crank it a little bit. I'm turning the crank in an electric generator. I'm doing mechanical work. Now the mechanical work has been stored as electrical energy, and I can turn on the flashlight. This one is really a cool device. It also has a radio and a siren. So that's a rather cool device that is powered entirely by muscle power, but the muscle power makes energy which then gets stored in the battery. Here's another example. This is a shake flashlight, and this one's a little easier to see how it works, because what's inside this shake flashlight is a coil of wire, a hollow coil of wire, and a magnet. And you can kind of see the magnet can go back and forth through the coil. And of course, the magnet's magnetic field is changing in the vicinity of the coil, or the coil experiences a changing magnetic field as the magnet goes back and forth through there, and that changing magnetic field generates electrical effects, in this case an electric current. And in this case, the electric current actually goes into charging a capacitor. Now, a capacitor is an energy storage device that can store energy for a little while, but not for a really long time. And so this is not a flashlight you can charge up and then leave sitting on your dresser when you need it in the middle of the night. You have to kind of shake it a while. And the magnetic flux through that coil is changing, and that's causing an electric current to flow in that coil, and that current is putting charge on the plates of a capacitor. And if I've shaken it enough, I turn it on, and it lights. So two examples. This is a rather different design of generators. Most generators are rotary devices where you spin a coil of wire. This generator, the magnet shakes back and forth. That's why it's a shake flashlight. I gave these out as souvenirs one year when I was teaching introductory electromagnetism to all my students on the final exam. But in order to keep their souvenir, they had to write an essay explaining how this thing works. And I'm pleased to say they all did. Works by electromagnetic induction. Well, let's get a little bit quantitative. Let's talk about how you might actually design an electric generator. Okay, so let's start with a simple loop of wire in a magnetic field B. The wire loop is initially oriented, so its perpendicular is here to the right, same direction as the magnetic field. The angle between them is 0. I'm going to call that angle theta. And we're interested in what's happening to the magnetic flux as time goes on. This loop is going to rotate. The flux through one turn of that loop is going to be the magnetic field times the area times the cosine of the angle between them. So as the angle increases, you can see the flux decreases for a while. That's because the number of field lines going through there is decreasing. There it is decreasing further. When it's perpendicular, it would be 0, and then it gets bigger again as the loop continues to go around. We're going to describe that motion as we did back in the lectures on rotational motion as theta increasing linearly with time. The rate of increase is omega, the angular velocity. And we want to know then how theta, equaling this linearly changing in time quantity, how cosine of that theta changes with time. And I'm not going to prove it. You could prove it using calculus. But the rate of change of cosine omega t is, in fact, minus omega times the sine of omega t. And let me try to motivate that. Here I have the red curve is the cosine of 2t. So omega is 2 in this case. And you can see that where the cosine curve is flat, that is, at its maxima and minima, it's not changing instantaneously, and that's where its rate of change goes through 0. Where the cosine curve is changing most steeply is where the sine curve has its biggest values, and I put the 2 here without the minus sign, so I'm showing you sine of 2t, 2 sine of 2t, not minus 2 sine of 2t. But here's the big point. Cosine turns into a sine when you figure out its rate of change, and it gets multiplied by this angular frequency because the more rapidly it's changing, the bigger the rate of change. So now we can go on and finish designing our generator. We're going to start with a 500-turn loop. We're going to give it an area of 0.018 square meters, so I've already figured out the area. I haven't told you its radius. It's spinning at 60 revolutions per second, an important number because that will make it generate 60 hertz alternating current, which is the kind of electricity we use in North America, although a real generator might have multiple coils and so it might be spinning faster. It's in a 50 millitesla magnetic field, and we want to know what its peak output voltage is. So we know that the induced voltage is always the rate of change of the magnetic flux, and now we've sort of figured out how to get that rate of change. That's going to be the magnetic flux, or rather the rate of change. The magnetic flux was BA cosine theta. That's going to be BA, and then the rate of change of cosine theta, and there it is. And I've taken the minus sign off because I'm just looking at the absolute value. So there's the rate of change of magnetic flux. The angular velocity is 2 pi times the frequency. That's because there are 2 pi radians in a full circle. We worked out this relationship earlier when we were talking about rotational motion. So the frequency is 60 revolutions per second. The angular frequency is 377 radians per second. And that's the natural measure, again, of angle, the radian. So we're getting there. We've got almost everything we need. Now, one other thing to point out. I asked, what's the peak output voltage? What's the maximum it ever gets to? Because this voltage is alternating. Spinning coils in magnetic fields naturally makes sinusoidally varying alternating current, which is why that's so common. One reason it's so common. The maximum value of sine is 1. So if I work out the peak value, I can take all my numbers, put them together, change the sign into 1 because I want the peak value, and I've got my 500 turns. Each turn gets this much flux. I got 500 of them. There's the area, there's the magnetic field, and there's the 377 radians per second, and that comes out to be 170 volts. And by the way, that is the peak voltage of the power coming out of your wall outlets in North America. You think it's 120 volts. 120 is a kind of average. It's a sinusoidally varying waveform that goes up as high as 170, as low as minus 170, and its average is about 120. So there is an example of how we design an electric generator, and again, I emphasize all generators use electromagnetic induction, and they provide most of the world's electricity. Well, let's look at what happens now after we generate electric power. Generating power using power at 120 volts isn't the most efficient way to transmit power, as we already saw when we were talking about electric circuits. How do we get to these high voltages, hundreds of thousands of volts we use to transmit electric power? Well, we use devices called transformers, and I have some examples of transformers here. First of all, I have a simple demonstration. In the previous lecture, I actually built a transformer. I didn't call it that. I put 2 coils hanging together on a rod, and I varied the current in one coil. We saw an induced current in the adjacent coil. That's a transformer. Here I have a better example of a transformer. It consists of 2 coils of wire. One of them's hooked up to an alternating current power source. The other one's hooked up to our meter. There it is. The 2 coils happen to be mounted on an iron core, and the reason for that is the magnetic flux gets concentrated in that iron, and that ensures us that all the magnetic flux that comes through the first coil also goes through the second coil. And those 2 coils happen to have, the yellow one has 400 turns, it's marked, and the blue one has 200 turns. And that means the voltage induced in the blue one, because of the changing flux from the yellow one, ought to be half. This is a step-down transformer, and if I reversed it and turned it the other way, it would be a step-up transformer. So let's see what happens. So I turn the voltage on, and I've got about 6 volts here, and I've got about 2.6 volts on that meter. So my step-down transformer is, in fact, working. It's taking the 6 volts and turning it into roughly 3 volts. It's not a perfect transformer. If I turn it around, I get a step-up transformer. This does not buy us more energy because we get less current out of it, and the product of current and voltage is electric power. So I'll turn this one on. I've got now about 6 volts again, and I've got 11 or so volts there. So now I've got a step-up transformer. And we use transformers widely throughout the power system to alter voltage levels. That's one reason we use alternating current, because alternating current makes changing magnetic fields, and changing magnetic fields make electromagnetic induction, so we can easily change voltage levels. So there's a quick look at how transformers work. They change voltage levels with alternating current. There's a primary coil producing changing magnetic flux. That induces voltage in a secondary coil, and this iron core that we have here concentrates the magnetic flux. And in principle, the output voltage should be to the input voltage as the ratio of the turns in the two coils. As you saw, it isn't perfect because not quite all the magnetic flux gets transferred, but we can make them pretty good. And here's some examples of transformers. Down at the lower right is a simple power brick that you might have to charge to power, say, your cell phone charger. In the upper right is one that might be a transformer in a stereo system or a television. At the middle left is a transformer that you'll see hanging on a power line pole near your house. It typically steps down 4,000 volts, or if you're in the country, 7,000 volts, to the 120 and 240 volts in your house. And the other two transformers you see there are big transformers at power substations that are transforming power throughout the electric grid. In fact, if you look at the electric grid, it looks something like this. What we do is we generate power, typically at tens of kilovolts at the generator at the power plant, tens of thousands of volts. And then we step it up. We send it over long-distance transmission lines that might have voltages as high as, say, 345 kilovolts or 365 kilovolts is typical. And at each juncture, you see the kinds of transformers that might be used. We step it down, say, on the outskirts of a city, transmit it at about 4,000 volts through overhead or underground lines in the city, and then that last transformer, the one you saw on the pole, steps it down to actually 240 volts at your house, and that's split into two 120-volt circuits. And then you see one of those circuits going to power a TV set, and inside the TV, there's a transformer that steps voltages down to run the electronics in the television. So there's an example of transformers, or many transformers, as they're used throughout the power grid. And again, they work by alternating current because it's only alternating current that is changing and making the changing magnetic flux and can therefore use electromagnetic induction. Okay, let me look at just a couple of other examples of things that are sort of like transformers. I got to brush my teeth. How does that work? There's no electrical contacts on this thing whatsoever. There's an electric motor in it, there are batteries in it, and what happens? Well, at the base of this electric toothbrush is a coil of wire, and when I plug the thing in, that is where the power is going. It's going to energize that coil and making changing magnetic fields because it's alternating current, and when I place the toothbrush there, there's a coil in the bottom of the toothbrush, and the whole thing acts like a transformer. And so I have contactless transfer of electrical energy. That is an example also of a transformer. Another example is a proposed charging system for electric vehicles. And you see an example here in which a vehicle is sitting over a coil in the roadway, and there's a coil in the vehicle, and that coil in the roadway is making changing magnetic flux in the coil in the vehicle, and that's making electric currents that are going in to charge the vehicle's battery. This is an experimental system. It has been actually, there's a prototype underway near London on the M25 roadway. It's not clear exactly how well this will work when vehicles are moving, but you can imagine building it in a stationary situation where you park your car in a particular parking space and you get it charged that way. So that's another example of using induction to transfer electric power. That thing becomes temporarily a transformer when you've got the car parked over the device. One other example, slightly related to transformers but a bit different, are so-called inductive transducers. A transducer is a device that converts some non-electrical signal into an electrical signal, or vice versa, like a microphone or a loudspeaker. In fact, one kind of microphone, not the one I'm wearing because this is capacitive, is a dynamic microphone in which a diaphragm, a ferromagnetic diaphragm, vibrates near a magnet, and near a coil of wire, and the magnetic field changes as a result of the motion of that diaphragm, and that generates a current which is analogous to the sound. In an electric guitar, you have a similar situation. A coil's wrapped around a magnet, and the strings of an electric guitar are steel strings. They're ferromagnetic. They alter the magnetic field, and that's how the sound is converted into electricity. Finally, you can do sophisticated things like measuring pressure with a diaphragm and a coil of wire, and pressure moves this diaphragm, and that affects the magnetic field, and that gives you currents that tell you something about the pressure. So inductive transducers are very much with us. Well, let's look at some other applications of electromagnetic induction, some of which will be familiar and some of which will be more obscure. Induction isn't just about making currents flow in particular circuits. Currents can also flow in bulk material, conductive material that's subject to changing magnetic fields. And I have here a demonstration of that. Here I have a thin plastic tube with nothing in it and a small spherical marble. The marble is actually made of steel and it's actually magnetized. I drop it down the tube and of course gravity accelerates it and it goes down at a great rate, an increasing rate. Here I have 3 cylinders, hollow cylinders, sleeves, made of conducting material. This one's made of aluminum, which of course is not magnetic. The magnet does not stick to the aluminum. This one's copper. The magnet does not stick to the copper. And this one is brass, which of course is also non-magnetic. So these are non-magnetic materials, and I'm going to put these sleeves around my tube. I'll put the aluminum one at the bottom. I'll put the copper one in the middle. And I'll put the brass one at the top. It doesn't matter. And watch what happens as I drop the ball. Here we go. Went fairly quickly through the brass, spent forever to get through the copper, and then went moderately quickly through the aluminum. What's going on there? As the magnet falls, it's creating a changing magnetic field, and that changing magnetic field is inducing electric currents in these cylindrical objects, conductors. And that energy associated with those currents is being dissipated as heat. The copper is the best conductor, so it gets the biggest currents. Where does the energy that ultimately gets dissipated as heat comes from? It comes from the only place it can, the kinetic energy of the fall of the magnet. And so the magnet is slowed down. That phenomenon is called eddy currents, currents in bulk material caused by changing magnetic fields, and it's put to a number of practical uses. Among those practical uses is eddy current braking. In eddy current braking, we actually have spinning conducting materials, like an electric saw blade, for example, or in this picture, like the brake hub on a high-speed train, a Japanese bullet train. And what we do is that spinning conducting brake, we turn on an electromagnet right near it, we induce eddy currents, and they sap the rotational kinetic energy, and the train comes to a stop. Japanese bullet trains were using that technology until 2007, when they got smarter and used another electromagnetic technology. They used that kinetic energy to turn electric generators and put the energy back in a battery instead of dissipating it as heat. So there's an example of eddy currents. We use electromagnetic induction also for airport security. When you walk through an airport metal detector, you use what's called, in most metal detectors, pulsed induction technology. In pulsed induction, there's a current pulse that generates a brief magnetic field, and if there are eddy currents occurring in metal on the person who's walking through the metal detector, those eddy currents slow the field collapse, and so that slowness is detected by electronic devices, and that's what sets off the alarm. We use induction also, or have used induction more in the past than today, in information storage and retrieval. When we do that, we store information in patterns of magnetization on ferromagnetic materials like tapes and disks. There's a coil in a so-called reed head that gets induced currents as the magnetic medium moves past the head, and those induced currents reflect the stored information. And the time variation of that current is what gives us the information content. And some bygone technologies did this: reel-to-reel tapes, cassette tapes, video cassette technologies. Not too long ago, many of you remember those, they all read their information through electromagnetic induction. And hard disks still look like this picture, used to read their information through electromagnetic induction. Today they all read it through something called the magnetoresistive effect, in which the resistance in that reed head changes rather than getting induced currents. So information storage and retrieval. And I'd like to end with the last example, and probably the most common. That is today's technology. We still use this, although it's on its way out probably. We use magnetic strips on the back of credit cards and other cards. and we swipe those strips past a little coil wound around an iron core, and we induce currents that take off the information that is contained in that card. And I want to end with a demonstration that shows what actually happens when you swipe your credit card. Okay, here I have an actual card swipe mechanism removed from a card reader. There's a little plastic channel that the card rides through, and behind it is a small coil of wire wound on an iron core, and a little gap in the iron core is right where the strip on the back of the card will slide by. I've connected this through a cable to this oscilloscope, which we will use to display the voltage that is induced by the card. So we're ready to go. We'll also look at that on the big screen. I've got the oscilloscope set to trigger off the induced voltage. We're in a very noisy environment here in the studio, so the results are going to be very noisy, and occasionally it triggers by itself off the noise. But here I'll try to make it happen with my card. So I've grabbed my credit card out of my pocket, and here I go. Okay. We have what looks like a nice trace, and let's talk about that. That looks kind of messy, but what you're seeing here is the beginning of a rising, quickly alternating voltage. It's going a little higher as I go along, which is an indication that I actually was accelerating the card as I moved it. And then when the card left the reader, we dropped back to this stuff, which is the unfortunate noise that's present, electrical noise in this studio. We think it's coming from some light dimmers. But this is the signal from the credit card. And let's take a closer look at it. So I'm going to expand that horizontal scale so we can look at what's in there. And you begin to see that we're not just looking at random noise. We're looking at a distinct pattern of ups and downs and ups and downs. And occasionally, you'll see deviations from standard down, up, down, up, down, up. There's one that's a little narrower. And there's a couple of them. And you can see variations. And those variations contain, in some way that I don't know, the information that's stored on my credit card. I'm not going to display the whole thing, because if you know that information, you could decipher my credit card, probably. The people who designed card readers had to be pretty clever, because the speed with which I swipe the card can't matter. And yet, because induction depends on the rate of change of magnetic flux, the faster I swipe the card, the bigger the induced effects. Furthermore, the frequency of these ups and downs is going to be more rapid as I sweep the card more rapidly. So none of that can matter for the information that's contained in the card. So somehow the information has to get stored in these varying patterns, which will appear no matter how big the voltage gets or how close those patterns get together, we'll still be able to see those patterns. So there's what's on my credit card, a little tiny piece of my credit card. When I changed this knob to make the time scale back where I started, there's the entire swipe of the credit card, but now we can't see much because those little information peaks are really crammed together. So every time you swipe a card, think about Faraday's law and electromagnetic induction, because that's what's doing the reading. Okay, let's wrap up with a summary of lecture number 37. And instead of giving you a verbal summary, here's just an example to remind you of the many, many devices in your everyday life that use electromagnetic technology. Electric power generation, the transformers that send voltages up and down, transducers like microphones, the less obvious eddy currents that are flowing in bulk materials, the security devices like metal detectors, and finally the information technologies, especially card swipers.